All right. So we're going to be presenting is space, time, attention, all you need for video understanding. And so this part of this title feels like a throwback to attention is all you need. And that's probably because this is another one of those papers that's going to explore the question, can we exclusively solve this problem, video understanding or classification in this case, exclusively building on transformers? And that'll be in place of like convolutional nets or things of that nature. So this presentation will be organized very similar to previous presentations. We'll have a brief introduction, then go over some related works. And in this case, we're going to be throwing back to VIVIT and doing a brief comparison because that'll make it easier to understand the rest of the content. Then we'll go over the different self-attention schemes that were proposed by our paper. Then we'll dive more deeply into some of the attention schemes that were gone over previously. Then we'll go over the experiments and results that are important, show why the model was accurate and fast. And then we'll have a brief conclusion. So Timesformer had the overarching goal of being a scalable video architecture that, again, exclusively used transformers. Up until this point, the field has been dominated by CNN architectures, whether that be 2D or 3D. And there's been a little bit of dabble in transformers, but mostly on a pixel level. Rather than like a patch level. And so the authors saw this VIT tokenization and they noticed how effective it was and wanted to explore how it would work in video. So for related works, the authors point out a couple self-attention networks. So these include things like non-local networks, a 2D self-attention mechanism, and hybrid CNN transformer networks. So things like DETR. And then, of course, we have VIT, which was the father of this patch tokenization technique. And then we also have VIVIT, which was explored in last Wednesday's presentation. And it should be noted that that came chronologically after this paper. So it is a little unique to include it in related works. And so here's a brief comparison. Both VIVIT and Timesformer go with this notion of factorization. It's very difficult to scale when you include every token in the attention, and so they're going to break it apart. And so VIVIT goes with this technique of actually trying to really go into the nitty-gritty of transformers and edit the different parts of the transformer architecture. So this is from model 4 of the previous paper. What they did was break out the dot product into 2 different heads. So we have spatial heads and temporal heads, each with their own learnable KVQ matrices. Our paper, on the other hand, takes a lot more of a simpler approach and basically just stacks these different transformers. And the only modification that's really made to the architect or the transformer itself is adjusting how or where the attention goes. And so with this factorization, it'll go through like time attention and then width attention. And as these keep building upon each other, the tokens will, in theory, become more context aware of each previous attention. The previous work also introduced a different way of tokenizing. So there's a uniform frame sampling way of tokenizing in which each token is just a patch from a particular frame. So you can see this token here is just represented by this patch in a single frame. And also this tubelet embedding, which is where the patch also has a temporal dimension in the back. And so Timesformer only uses this uniform frame sampling. It is strictly just, let's take VIT, this 2D patches, and let's just try and make it work with video. So these are the 5 different attentions that were explored by our paper. Most of these architectures that are listed here are pretty similar. They all have these skip links between various different layers to preserve information, and they all end with an MLP. The important distinction is just the type of attention they're using and how many transformers. So these 2 networks have 1, these 2 have 2, and then this last one has 3 here. First, we have space attention. With this one, there is a single transformer, and it just does space operations. And so here's a figure from the paper. And what this shows is this blue spot here is the query token that we're interested in. And so it will attend to all of these colored tokens here, and this color will match this down here. And we've also rendered out some 3D views. And so we can see this frame right here, this 2D frame corresponds to this 2D frame in this little 3D clip. And so this will be helpful for visualizing, and I'll be using these to kind of show the attention. So this is space attention. this query token will attend to all of the tokens in its current frame, and that's it. Nothing in future frames or previous frames. Next, we have joint spacetime attention. This one has a single transformer block, and you can see it covers pretty much everything. So if we go to our 3D view, we have the query token, and it attends to literally everything in the clip around it. Next, we have divided spacetime attention. This one will start out, this is our first two transformer network, so it'll have a time attention and a space attention, and these are separate. And so if we have our 3D view and our little clip view here, it will first look at this time, which is green, and then look at space, which is represented by the orangish color. So we have time attention, which is done first, and then we have this frame attention, this spatial attention, which is done second. This also ended up being the most accurate that they were able to build, and it also has the benefit of being scalable because it doesn't need to use every single token in the entire video like the previous one. And so this network here we'll be exploring a bunch later in the presentation, and we'll also be exploring this one a bit more and doing some comparisons. Next, we have sparse local global attention, another two transformer network, or a two transformer block, because there could be more than one transformer in a particular block. So we have local attention followed by a global attention. The local attention is represented by this yellowish color, and the global attention is represented by this purplish color. And so here's our rendition. It will attend to all of these yellow tokens first, and then it will attend to these purple tokens in a more global area. And you can see from the front view here that the purplish areas cover over or like half of the image away. So they're a lot more global in nature. Finally, we've got the axial attention. And so a similar attention was explored in other papers, but on a pixel level, as opposed to a patch level. And so this is re-exploring that idea, but with patches. So we've got time with height. Again, we have the time in green, width in this yellowish color, and then height in this purplish color. So we've got, it'll attend to time first, then width, and then height. Here's a comparison between the different options that were just explored. So the two space and joint space time each have a single transformer block. And so they've got about 85 million parameters each. The divided spacetime and sparse local global each have two, so they've got a bit more at about 120 million. Then this axial attention has three, the most, and so it's got the highest number, which is at about 155 million. On the K400 data set, they all do pretty well, although divided spacetime does the best. Something to note about this data set is spatial cues are very helpful, so any model that can capture spatial relations will do pretty well. SSV2, by contrast, you need temporal cues in order to really get accurate. So this is where the first one really starts failing and only has an accuracy of around 36. The rest of them, which do include temporal attention, do pretty well, again, with divided spacetime clocking in at the best, followed closely behind by joint spacetime. I will now be passing it over to Matt to get into the details of the architecture.
So when referring to the timesformer model, we're talking about the divided space-time attention model. So as seen in image transformers before it, we've got height times width times 3 RGB values. And then the timesformer adds the temporal dimension of a clip comprised of MF frames. So 1, 2, 3. And we also decompose into patches, just like VIT. Of size P times P, 16 times 16, 14 times 14, whatever you want. And as you'll see in the next order formulas, the patches are flattened to vectors. Our vectors are X with the spatial index P and the temporal index T. And this is sort of just an illustration, just showing the patches as you've seen before. So for the linear embeddings, each patch is linearly mapped into an embedding vector Z. Of size D, D being all of the tokens plus the classification token. This is done by means of a learnable matrix E. If you happen to remember last week's VIT, they introduced new embedding, as Ryan sort of already talked about. Timesformer uses uniform frame sampling, while VIT used tubelet embedding with central frame initialization. This is just the patch that we just talked about, again with P space and then T time. And then our learnable positional embedding to encode the spatiotemporal position of each patch. And so Z0 here, that just means it's our first embedding token. And Z000 is going to be saved for it's going to be allocated for the class token essentially. And overall, the matrix of the embedding token Z becomes the input to the transformer. So now our query key value computation, there are L encoding blocks, and we go over every L encoding block, and we calculate a query key and value vector, and it's encoded using the preceding block. Like I said in the past slide, we calculated Z0. So that's gonna first come in here, and then from there on out, this will continue to feed itself. So we are going to go over every encoding block L, right, and each attention head A. W is our learned query key and value matrices, and then we do some layer normalization to reduce the training time. We do that layer normalization on the preceding block as talked about. So with the size of Z being D as discussed, and we're going over A attention heads, the dimensionality of each calculation is going to be D divided by A. So pretty much dimensionality of Z divided by the amount of A's, DH, sort of explains itself. So yeah, and basically all of these steps are identical for queries, keys, and values. So this is sort of our general equation. You can think of this as the joint space-time equation. It calculates the dot product of the queries and keys. So starting out, we've got the queries. The transpose is necessary to compute the dot product and compute all combinations of the queries and keys. Now let's talk about the keys. So this is a little confusing with this paper, but essentially this is the keys, right? This very first block right here, it's the key classifications, and it's concatenated with the set of keys. And now this is the set of keys, notice the braces, and it iterates over patches in all of the frames. So again, it's the classification key is concatenated with the set of all keys, and then it is dot product with the queries. And DH is sort of just this basic normalization that you'll see. And one thing to note is that this equation has n times f plus 1 comparisons as it goes through NF, all combinations of patches and frames, and then it adds on the classification token. So that's sort of that plus 1. Now to sort of reduce the n times f plus 1 complexity, we are going to reduce it by splitting it to space and time. That's the divided space-time model. Now the attention for time is computed and then is then fed into this attention calculated for space. So first we compare each patch with all the other patches at the same spatial location in the other frames. And then we feed that to calculate the spatial attention for all of the patches. So it goes time, then space, then the MLP. Previously in the transformer model, as I just discussed, we considered space and time simultaneously. That was n times f plus 1, right? Now it's n plus f plus 2. And the reason for this is n comparisons plus f comparisons, right? But you got to remember the plus 1 here and the plus 1 here. So it's n plus f plus 1 plus 1. So we get n plus f plus 2. That is the reason why it is faster. It is less comparisons.
So those are the CLS tokens, right? The additional 2.
Yes, yeah, the classification, yes.
Mm-hmm.
And so from here on out, I'm going to sort of just blow through it because this is something that we've already seen in every other transformer. So at each encoding block L, the last slide was us computing these self-attention coefficients, right? So we compute the weighted sum of value vectors, and then from there it passes it to the MLP. And then we obtain our final classification token, and that one hidden layer MLP is appended for those final classifications. So now I'll pass it off to Nate to start off the experiments for us.
So I'm going to be going over some experiments and results. I'm not going to get too far into detail, but I just wanted to point out some observations that we had from some of the graphs and tables that show up in the paper. So the Timesformer was evaluated on mainly 3 data sets, and those data sets are Kinetics 400, and that is a data set that focuses a lot more on spatial cues over temporal cues. It has around 160,000 10-second clips from YouTube videos and 400 classes, hence the name Kinetics 400. The second data set that we're going to take a look at is the something v2 data set. And that is a data set that focuses a lot more on temporal cues rather than spatial cues. So there's kind of that notion of the 2 different kinds of data sets. And you noticed in some of the results that were already shown, SSV2, the accuracies were not quite as high as they were on K400, and that's because there's a lot more complex patterns in the temporal dimension for the Timesformer to learn. So the accuracy is a little bit lower, but more on the SSV2 is it's around 220,000 videos of people doing things with objects. It's an action recognition data set, has 174 classes. And then the last data set that we're going to be going into is the diving 48 data set. So that's another temporal data set. It has 18,000 fine-grained videos of competitive diving and 48 action classes, hence the name diving 48. So the next thing that I want to highlight is just the accuracy, training time, and computational complexity of the Timesformer. And this is specifically as it relates to 2 different pre-training data sets. So the first one, ImageNet 1K, and the second one is ImageNet 21K. And if you take a look down here, this is where the Timesformer is. You can see that it does very well in training time. And this is that divided space-time attention model. So very computationally efficient. It gets a really competitive training time, really low inference cost as well. About half of the lowest one that they compared it to, which was i3D. And it also has a massive number of parameters in relation to the other CNN-based models. So that kind of highlights how efficient that divided space-time attention model is. And you can see that in this context, pre-training on ImageNet 21K actually had a pretty significant impact on the accuracy on the Kinetics 400 data set. So that's kind of shown here where on 21K it achieved an accuracy of 78%. And that ImageNet pre-training, the dimensionality of the data is 8 frames by 224 pixels squared. And those are that's the size of the video clips. And then it's important to note as well, right here, it kind of shows up. The authors didn't have access to a ResNet that was pre-trained on ImageNet 21K. So this, the most accurate slow fast model was actually not pre-trained, but it was just trained for 6,300 hours. Okay, so then the next thing that I want to kind of go over is the impact on the number of training videos on the accuracy on both data sets. And we're going to kind of look at those. Remember, something v2 is much more temporally focused and Kinetics 400 is much more spatially focused. So if you look here on the left, you see Timesformer is doing great right off the bat, and it outperforms both of the compared CNN methods. But its accuracy does rise steadily as you increase the number of training videos. Now, if you take a look at the right-hand side, you see a different story. The Timesformer is actually not doing as well as the CNN, as the compared CNN models until you reach around 127,000 training videos. And these ticks on the bottom aren't chosen arbitrarily. Those represent 25, 50, 75, and 100% of the data set. So you can see that because something v2 is much more temporally focused, it actually takes a lot more data for the Timesformer to start performing at a competitive level. So this is something I want to go over. It's kind of just a comparison of the 3 different variants of the Timesformer and how pre-training affects their accuracies. So the first one is the base Timesformer. That's the one that I already mentioned. It's 8 by 224 squared. And you can see the accuracy here is really good, and it was competitive, and I'll show that in a little bit. The second one that I want to go over is the Timesformer high resolution. So that's 16 frames by 448 pixels squared, and so it's a lot more data because it's a higher amount of pixels and a higher amount of frames as well. And then the last one is the Timesformer L, and that one is 96 frames by 224 squared. So that's, again, a much larger amount of data, and that's actually the best in class performance that we see from Timesformers. And it's interesting to note as well that the ImageNet 21K pre-trained models work better on K400. There's a large increase in accuracy on all of them. But if you look at SSV2, it's not really a change. It's minuscule at best on the Timesformer HR, and it actually decreases in accuracy on SSV2. And that's because of that temporal focus that we kind of got into earlier. So, and now I want to go over some accuracy in terms of the spatial crop size. So basically, during inference, what they do is they take 3 spatial crops, and that's going to be from the top left of the image, from the center of the image, and from the bottom right of the image. And this top graph kind of shows the accuracy in terms of that spatial crop size. And you can notice that the highest accuracy attained comes from 448 pixels squared. And that's why that was the high resolution variant of the Timesformer, rather, because there's a sharp drop off after 448. And you can see down here as well, this kind of gives a rationale, like in terms of performance, for why divided space-time was used so heavily in this paper. You take a look at joint space-time, which is, again, comparing every single patch to every other patch in every other frame. That's a lot more computation, n times f rather than n plus f. So you can see that it scales pretty poorly as the spatial crop size goes up, and it actually runs out of memory right around 448 pixels squared, whereas the divided space-time Timesformer actually scales really well with the size of the image crop. Now, on the right-hand side, I want to highlight the number of input frames as it affects the accuracy. So that one is pretty straightforward. As the number of input frames goes up, you see the accuracy go up, and that was kind of reflected in the fact that we got best-in-class accuracy from Timesformer L because it handles 96 frames. So it's a lot better at picking up on temporal relationships. And down here, again, same story as on the left. You can see we're out of memory past 32 input frames with the joint space-time method. And that's going to be down to that multiplying rather than adding in the computational complexity. And you can see divided space-time scales really well out to 96 input frames. So this graph is kind of interesting to look at because it answers the question of, given one spatial crop, how many clips, how many input, a number of testing clips are needed during inference. And so you can kind of see the Timesformer L is pretty stable. It doesn't really care how many testing clips you throw at it, whereas the CNNs and the base Timesformer kind of experience an increase in accuracy up to around 5 testing clips, and then it kind of levels off. And it should be noted too, the Timesformer L can handle 12-second long clips. And then the last table that I really want to show as it compares the variance is this table is kind of showing the comparison of the Timesformer variance to a bunch of other CNN-based methods. And you can see really nothing super crazy going on here, but it is a slight increase in accuracy for the Timesformer L. That's your state-of-the-art performance on videos. You see here top 5 accuracy. Again, all of them are competitive, but the best in class comes from the Timesformer L. That's that long-range model. And then here, you see that the inference cost is actually the lowest number of teraflops when using the base Timesformer model. And that's because of it only has that 8 by 224 by 224. That's a lot less data than 16 by 448 or 96 by 224. So that's kind of to be expected. So in cases where performance is critical, you would use the base Timesformer because it gets acceptable accuracy with a very low inference cost. But if performance isn't too much of a consideration, the Timesformer L gives best in class accuracy. So now I'm going to go ahead and hand it over to Crystal, and she's going to finish up the experiments and results section.
So they also compared SSV2 and Diving 48 to CNN models and Timesformer. We can see that for SSV2, once again, Timesformer L and Timesformer HR outperform SlowFast. However, in this case, Timesformer does not have a state-of-the-art accuracy. It is outperformed by several CNN methods, but it is still competitive, which is important to note that Timesformer is doing fairly well on such a temporally difficult data set. For diving 48, Timesformer L and Timesformer HR do outperform SlowFast, which again shows some very good performance on a very temporally heavy data set. Then we have a TSNE comparison on SSV2. We can see that there are more separatable features with divided space-time attention. Each of these points is a video, and each of the colors represents an action classification. So for VIT, we can see that these features are not very well separated, and there's not a lot of clustering. Then when Timesformer with space-time attention, we can see that the clustering is quite improved, particularly in these regions here. We can see it here. Then with divided space-time attention, the features are even more well separated, and we can see a good representation in these areas amongst some others. Now, they also evaluated Timesformer on How to 100M. It is a long-term video modeling data set with 1 million instructional videos across 23,000 task categories. The average video duration was 7 minutes. They selected for their experiments only tasks that had at least 100 videos, which left them with 120,000 videos across 1,059 task categories. They randomly selected 85,000 for training and 35,000 for test. And here are their results. For SlowFast and Timesformer with 8 input frames with a single clip covering 8.5 seconds, then an input of 48 clips, we can see that Timesformer outperforms SlowFast by approximately 8%. When they increase the number of input frames to 32, thus increasing the single clip coverage to 34 seconds across 12 clips, we can see that Timesformer outperforms SlowFast by about 11%. That trend continues when they increase the number of input frames to 64. However, when they increase the number of input frames to their maximum value of 96, we actually see that SlowFast decreases in accuracy by about 0.3%, while Timesformer continues to increase in accuracy. There are some advantages to Timesformer. The reported accuracy is comparable, if not better, than most state-of-the-art CNNs. It is more efficient than comparable methods requiring less T-flops. There is a higher number of learnable parameters than state-of-the-art methods, and it is better able to capture time dependencies than 3D convolutions. It captures longer dependencies and is not reliant on composing smaller actions into larger actions like CNNs. There are also some disadvantages. Just like other transformer-based architectures, it requires pre-training or a large data set. The attention mechanism is limited in time, and for this model to cover 7 minutes, the clip must be sampled and have the results averaged. And then to finish up, I would like to compare Vivit's results and Timesformer. Vivit outperforms Timesformer L on the Kinetics 400 data set by about 1%, which we can see here. But it requires 1.67 times more teraflops for the same number of spatial views. And we can also see that Vivit is able to achieve a similar accuracy, about 0.1 less, for a less inference cost if they cut down the number of spatial views.